So we continue with the second part of this chapter, which is 5.2, which is the conservation of mass. Okay, conservation of mass actually, it is one of the most fundamental principles in nature, and it's quite straightforward and easy to understand. And you don't have to be a rocket scientist to know the mass of, like for example, 100 gram of flour plus 100 gram of water. For sure, it's going to be 200 gram of the mixture, or we can do maybe. So for sure, it's going to be 200 grams. So conservation of mass, mass is like energy. It is conserved property, and it cannot be created or destroyed during a process. And closed system is where the mass of the system remains constant during a process, and differently for control volumes, the mass can cross the boundaries, and so we must keep track of the amount of mass entering and leaving the control volume. So for this kind of case, the M in and M out is not necessarily need to be the same. Okay, mass that gets into the control volume and mass that goes out control volumes, unless it is a steady case. Okay, in a steady flow, the M in equals to M out, so the change in mass in a particular time remains constant. Okay, this example where you have this mixture of 2 kilograms of hydrogens and 2 kilograms of oxygens. Okay, it will give you 18 kilograms of H2O. But as you know that the volume might be different because hydrogens and oxygens both are gases, and H2O is liquid water. But as for sure, the things that for sure, mass need to be conserved. And mass and energy, it can be converted to each other. This very popular equations formula found by Albert Einstein, where E equals to mc squared, where C is the constant of the speed of light in the vacuum. So here it talks about the mass and volume flow rates. Mass flow rates is the amount of mass flowing through a cross section per unit time. So cross sections here is the AC, as you can see here, and this is the velocity, how fast the velocity going across this surface, and the product of this V velocity and area actually will give you the volumetric flow rates. It will give you the velocity flow rates. Okay, and this is density. So as you know that density, when multiply density with volume, you will get mass. So just keep in mind that this V is velocity, not volumetric flow rates. You need to be familiar with this because this is going to be used quite sometimes. Where V with the normal V capital, this represents the velocity. Meanwhile, this V, which is quite big, is quite similar to U a little bit. That is a wider V. This is a volume. Okay, and this one, another one. This is kinematic viscosity. Okay, this you're going to see this quite a lot of time. Kinematic viscosity as you advance into later chapters. Okay, these point functions have exact differentials. Actually, this just explains the difference between the terms. This D, this is used for path functions, and it has a exact differentials. Okay, D like this actually used for as mentioned here is point functions. It used for properties, and this del is used for path functions, and it has this inexact differentials. And this kind of, for example, of other quantities that use these path functions is heat other than mass transfer. And when you want to find this V, actually this V is not just simply the velocity that goes past or cross this control surface area, but it's actually is Vn here is the velocity in the normal components or perpendicular components to the surface. So this is your surface, and at this surface this is the normal component with 90 degrees. So Vn here is the velocity, the normal velocity actually. So like for example, you are given the velocity at a certain angle, for example, so you just need to find the normal velocity with respect to the surface. Okay, this is like the equation that you seen before, the differential mass flow rates. Okay, usually more of the time we will give you like the area straight away instead of asking you to do the integrations. So most of the problems just require the simpler versions of the equations where the mass flow rate is equals to rho v times a. Okay, but you know that the v actually is other than is need to be normal with respect to the surface, you also need to make sure that the v that you obtain that you use is the average velocity. Like for example, here you can see in the figure below, due to the no slip conditions, the velocity at different height is different. The velocity at the center is higher. The velocity at the wall is for sure is equal to zeros because it's a no slip condition. It's equal to the velocity of the wall itself. If the wall is static, doesn't move, the velocity is zeros. So you cannot just simply use velocity at any point. So what you need to do is you need to find the average velocity. And how do you want to find the average velocity? Okay, here is the average velocity up there. Okay, basically this is we assume that this is a two-dimensional. Okay, so what we have that usually in the previous chapters we learned that the velocity can be expressed as a function of location or height. For example, here you have like for example y and x. So v can be as a function of y. Okay, sorry for this. So it's a function of y. So this is a two-dimensional. So you can just assume that the z direction, for example, equals to only 1. The width is equals to only 1. So you can just change a here with y. Okay. So it depends on the number of dimensions that you are dealing with. Okay, so what you have to do is first we have this velocity profile. From the integration, basically what we are going to obtain is the area under the graph. Okay, and then you just need to divide with the area, or in this case with y, and then you get the average velocity. Basically, this is how you want to find the average velocity. Okay, some of the cases, some of the problems, some of the questions in the textbooks, this average velocity is given straight away, and sometimes if you found that okay it's given in a form of equations, you need to make sure that the one that you are using in this mass flow rate equations, it needs to be average velocity. Okay, so basically the same. So basically volumetric flow rates equals to average velocity times the cross-sectional area. So this is for example the cross-sectional area, and this is the velocity, this long. So basically the multiplication of it will give you the average velocity, the average volumetric flow rates. And this is the conservation of mass principle for control volumes. Okay, actually the net mass transfer to or from a control volume during a time interval delta t is equal to the net change, increase or decrease in total mass within the control volumes during that specific periods or durations of time. So basically this is explained by this. Okay, this is just the mass that comes in minus the mass that goes out equals to the change of amount of mass. Okay, the picture with the bathtub below actually explains that. Okay, let's say that in that specific duration of time, you supply 50 kilograms of water into this bathtub, and at the same time you open the drain pipe, and at that specific time it can only allow 30 kilograms of water to go out. So basically the amount of water during time is increased by 20 kilograms because in is higher than out. Okay, that is if you we represent it in terms of mass. So the on the right side of the equation on the right actually is shows the rate of change. Okay, the rate of the mass that goes into the bathtub minus the rate of mass that leave the bathtub is equals to the mcv over dt. So if it is positive, that means that the water increasing. If it's negative, it means that the water decreasing. So this mass balance is applicable to any control volume undergoing any kind of process. Okay, basically this equation actually is quite similar to what we've seen before. Basically, we assume that the density always constant for any particular, like for this one particular case. So whatever change in volume will cause the mass to change as well. So the total mass within the control volumes is defined as this. So the mass is equals to the summation of this density for this function of v. So the rate of change of mass within the control volumes need to differentiate the equations above with respect to time. And normal component of velocity, as mentioned before, that this is normal component Vn. And how to get Vn, like for example, given if you look at the figure below, the velocity is given at like a certain angle from the surface. It's like the alignment of my hands is very. So this is theta with respect to the normal components, to the normal axis. So for you to get this like Vn, you just need to find equals to v cos theta. Okay, but in most of the cases, this Vn will be given straight away. We seldom give the textbook seldom give you the problems with like given at v at different theta. So usually just give you the Vn straight away, and n here actually is represents the directions. Okay, whether it's going to, either it's entering or it's leaving the control volumes. I think the more details of this n will be explained in I think next couple of slides. I think. So differential mass flow rates. Mass flow rates equals to v. You have seen this. So Vn here is equals to v cos theta, and v cos theta also represented by Vn. So net mass flow rates is this is the mass that going in and leaving the control volume actually. So it's described by this. Okay. So basically when we take into account like we combine all the terms together, basically this will give you the general conservation of mass. And actually it is similar to what actually we have seen just now. This is just like another way of how to express the equations, or actually to express the conservation of mass in a controlled volumes. So what actually we have here, the term on the left here, it actually represents the rate of change of mass in a control volumes with respect to time, where you can see at the bottom one, see, this is the same thing. And on the right side, on the term on the right, actually this is the net mass flow rates, which is, it shows give you the difference between the mass flow rates that get into the control volumes minus the mass that goes out from the control volume. So this is basically comes from the right terms on the general conservation of mass. Basically, this is the same thing. It's up to you whether which one actually is you prefer to remember. But I believe actually the bottom one is the most simplified versions of the equations. And actually these things has been discussed in chapter 4. If you look back, the Reynolds transport theorems, which is quite similar, where this B and this small capital B, actually they are representing any properties, and you can just change with any properties that you want. If you want to talk about the conservation of mass, just simply substitute B with M, and here with the lowercase b is actually is the same as the capital B per unit M. So if you change B equals to M, so meaning that if you want to change B to M, what it's going to be is this will becomes M over M. So that's why you have B equals to 1, because mass per mass unit per unit of mass, so it becomes 1. Okay, so it's not necessary for you to really understand that. Actually, the most important thing is at least you know how actually it's being derived. Okay, for moving or deforming control volumes, okay, there is some special case where you have this control volume, so it's changing its shapes or it's moving. So for this kind of case, there's a slightly special way how to deal with it, where instead of dealing using the absolute velocity, we need to use relative velocity (VR) instead. So this is important. It will make the calculation much more easier if you use this. There are several problems and examples in the textbooks you discussing about this moving and deforming control volumes. We are going to discuss that in the future in our tutorials class, in the live sessions, so that it can give you much clearer view on this instead of like reading from this text. And mass balance for steady flow process. Okay, so there's a keyword here. Basically, this term is very important. Whenever you see this term, there's something that need to comes into your mind, where it doesn't change. This is something that doesn't change with time. Okay, so when you say during a steady flow process, the total amount of mass contained within a control volume does not change with time. Okay, for this case, the one that doesn't change with time is MCV. So meaning that the MCV over dt equal to 0. So MCV is constant. So like we have a steady flow, fluid flow. Before this, we learned that du over dt, it needs to be equal to 0 if for steady flow. Okay. So the conservation of mass principle requires that the total amount of mass entering a control volume equal to the total amount of mass leaving it, regardless how many inlet, how many outlet you have. Okay, like for example, in this figure on the left, you can see that there are 2 inlets, and okay, the one that on the first inlet, 2 kg per second is coming in, and 3 kg per second of fluid comes in from the second outlet. So the outlet only one. So from these 2 inlets, you can find how much is leaving per second. So it's just total of M1, M2. It needs to be 5 kg per second. Okay, this is steady flow. This is just to make sure that the dm CV over dt is equal to 0. Okay, unless it is not equal to 0, the one that comes in not equal to the one that comes out. Okay, so basically M1, the mass flow rates, okay, this is not really representing this figure. Okay, this is not this is like the one in the 1, 2 and 3. Okay, the one that actually 1 here means that in the mass flow rates in equal to mass flow rates that goes out, or go in, V in, A in equals to go 2, V2, or go out, V out, A out. Okay, this is for single stream, meaning that you have 1 inlet and 1 outlet. So there are many engineering devices such as nozzles, diffusers, turbines, compressors, and pumps involve a single stream, which has only 1 inlet and 1 outlet. Okay, actually among these devices, the one that is quite interesting is compressor. Okay, like the rest usually the density remains constant most of the time, ideally. But compressor, actually the term itself, the compressor term itself means that it compress. It makes the density much bigger. Okay, for this kind of case, you can expect that the density that leaving is higher than the density that entering. So for compressor, usually O2 larger than O1. Okay, this is a special case, which is incompressible flow. Okay, as I mentioned previously, in fluid mechanics, most of the time we are going to deal with incompressible flow. So when we talk about incompressible flow, okay, actually you can see that the conservation of mass relation can be simplified even further when the fluid is incompressible, which is usually the case for liquids. Is because like fluids, it can be either gas or liquids, and gas, it is highly compressible, can be compressed easily, but compared to liquids, liquid is quite hard to be compressed. So that's why incompressible flow usually it applies on liquid flow instead of not gas flow. So for this, since the density remains unchanged, you can just say that volumetric flow rates that comes in equals to volumetric flow rates goes out. It is because we have it before, M in equals to M out, so rho V in equals to rho V out. So since the density remains constant, that's why we have this V in equals to V out. Okay, and also from there we can get the simplified versions of this. So before this we have density, now we don't have density, and there is no such thing as a conservation of volume principle. Okay, it seems from here, from this equation, it looks like it is a conservation of volume, but no, it's not. It's just a special case where the density remains unchanged. One thing for sure, this is basically due to the conservation of mass. Okay, conservation of mass always happen, but not conservation of volume. Okay, conservation of volume only for special case like this, and this is actually not even the principle conservation of volume principle. This is conservation of mass, but with a constant density. Okay, and from the figure on the left, this is an example of the case where the flow is compressible. Of course, you can see the word itself, compressor and compressible. Okay, from this you can see that the mass flow rates in inlet is 2 kilograms, the mass flow rates at the outlet is 2 kilograms. Okay, it fulfill the conservation of mass principle. But how about the volumetric flow rates? Different. Now the volumetric flow rates that coming in is 1.4 meter cubic per second, and the one that going out is lesser. So from here, what actually we can conclude is the density at the inlet is lower compared to the density at the outlet. It is being compressed. It being compressed, that means that the density becomes higher. Okay, this is an example of the way on how we want to measure the volumetric flow rate. Okay, like given that you have a 40 liter bucket, okay, you are given this bucket is 40 liter, and then you have a nozzle, you have a hose with 2 centimeter diameter, and then you have a nozzle exit of 0.8 centimeter diameter, and then it takes like 50 seconds to fill the bucket with water, and it asks the volume and mass flow rates of water to the hose. So basically you already know the volume of the bucket is 40 liters, and it takes like 50 seconds to fill in. So basically the difference, the divisions of this 40 liter over 50 seconds will give you the volumetric flow rates. Okay, so it gives you 0.8 liter per second. And then you have this volumetric flow rates. How you want to find the mass flow rates? Okay, you know that the density of water is 1 kilogram per liter. So from there, you can get the mass flow rates. Okay, just multiply the density and the volumetric flow rates. And then it asks the average velocity of water at the nozzle exit. Okay, as you know that the volumetric flow rates is equals to the velocity times cross-sectional area. So the first thing that you need to do, okay, you have V already, tick, and you can find the A. Area is already given, the diameter, tick, so you can get V. V equals to volumetric flow rates divided by A. So here we get the volumetric flow rates is 0.8 liter per second. The area at the exit is equals to this, as mentioned, the pi r squared. Okay, it's 0.5027 times 10 minus 4 meters squared. And it gives you the velocity of the liquid at the exit is 15.9 meter per second. Okay, and these are some additional information that the average velocity in the hose with the 2 centimeter diameter, you get it's looking from this equation, similar equations, the V equals to volumetric flow rates times the area of the hose. With 2 centimeter diameter, you get 2.5 meter per second. So from there you can find out that the nozzle increase the water velocity by over 6 times.